in first period I had to take a picture, which wasn't terribly helpful. All right, so what's the limit as x approaches 0 from the right? So I've got a piecewise function. In piecewise functions, if you're interested at x equals 0, the breaking point of 0 is between these two functions. So when I plug in 0 to this thing, I get 0. When I plug in 0 to this thing, I get 0. I could graph it, but I really don't need to because I know as I'm coming from the left and the right, it's going to 0. So this is going to be 0 because it's going to the right. Since we're going to both to the same spot, this is also going to be 0. Notice neither of these are equal to. So if you were to graph this, when you get to x equals 0, there would be a hole, but limits don't care about holes. They just care about where are we both going to the same y value. What's the limit as x approaches 1? Well, if x is approaching 1, we're in this function's area. So I plug 1 into this, and I get 1. Next, what about my limit as x approaches 2 from the left and 2 from the right? Well, if I'm approaching 2 from the left, we're in this area. So I plug a y value, I plug 2 here, and I get 4. When I plug 2 into this, I get 8 minus 2, which gives me 6. So while the limit as x approaches 2 doesn't exist, I don't ask that. I ask what happens if we go from the left, which is going to give me 4, and as I come from the right, this is going to give me 6. Oh, and I do ask, what's the limit as x approaches 2? Well, since those are different, I get to say does not exist. So here's a piecewise function with limits. Any questions? Okay. I don't actually remember teaching this, so that means I probably didn't. So I'm going to kind of teach it now as far as these go. Whenever you see limit of something, basically you can just, this means f of 2 is equal to negative 3. So if you ever see f of x or g of x, particularly when you're plugging in here, those are y values. And I'm telling you the y value for this one's negative 3, and the y value for this one at g is 5. So you effectively just plug it in. So while the notation looks ugly, actual practice is not so bad. This is modified from a multiple choice question from 1 year, and I really like it. So I'm going to give you a few minutes to think about this, and when you finish these, or give up, do the little hand raise. Because I want to make sure I have time to do everything else. So these first ones, again, apologize. I don't remember teaching this, so I may be just teaching it now, but the way you approach this, if I tell you the limit as x approaches 2 of f of x is equal to negative 3, I'm telling you your y value is negative 3, right? So anytime I see f of x at 2, I know my y value is negative 3, and this is telling you your y value of g of x at 2 is equal to 5. So basically, since I'm going to 2, I'm going to plug in my y value of f of x, which is negative 3. I'm going to plug in my y value of g of x, which is 5. So this is 2 times negative 3 minus 3 times 5. So minus 6 minus 15 gives me negative 21. Same thing happens here. Let's see, that's going to give me 25 minus negative 3, so I end up with 28. So as far as your limits go, just plug in, it's just a fancy way of saying plug in your y values. This next question, this I like. This is interesting. And the reason it's interesting is this is sort of testing how well do you, like, I haven't given you a question like this, right? Yeah, in homework, and to be fair, when they ask something like this on the AP exam, they know that they're trying to see how well you understand concepts. And one of the things I have to teach in this course is what do you do when it looks weird? And the first thing you should always try to do, draw a picture. No. Whenever you're given a situation and you have zero clue or you're really confused about what's going on, draw a picture, because sometimes when you draw the picture, the answer's obvious when you see a picture. It's hard to see what's going on here. And I know some of you are obnoxious and you say, well, I got it right and I didn't draw a picture. And I said, yeah, you did. You just did it in your head, right? But like the only way to do this problem is draw a picture. So if I give you a chart, particularly when it's only a few points, plot them. And it says at 2, I'm at 2, okay. I get a dot. At 3, I'm at 5. At 4, I'm back at 1. And I say something. I said f is continuous, and it says, does f of x equal 3 have at least one solution? Does it have 2 solutions and why, right? Well, when this says f of x equals 3, they're saying, does the y value ever equal 3? Meaning, if I were to connect those dots, does it cross that line? Right? Now, because you have to connect the dots. I said it's continuous. If it's continuous, you have to connect the dots. Well, so now when you look at the picture, like if I gave you this picture and I said connect the dots, does it cross the line once, twice, right? It's an easy question. But if you haven't drawn the picture, the camera has this autofocus. If I get too close, here, I got it out of the way. Come on. 1, 2, 3. Come on. Switch. There we go. All right. So now if you got to connect the dots, you say, well, okay, it's got to go up, it's got to go down. All right. It has to cross at least twice. But you have to be able to interpret your picture, which I think is kind of interesting. Now we're getting into some of the stuff we've talked about. Is that here? Yep. All right. Yes. So now let's do the next set. Actually, we'll pause just for a second. Similar to one that we just did. And this says, what happens as x gets really, really big? Well, as x gets really, really big, you have to ask yourself, it doesn't matter if there's a trig function or anything else, you're focusing just on that fraction part. And when you focus on that fraction part, you ask yourself, what's important? Well, what's important on top is the only thing that's on top. It's a pi times x. What's important on the bottom? Well, that 2 doesn't matter. When x is huge, the 2 doesn't matter. So what's left is a negative 3x. Well, now can you simplify this? Yeah, you can simplify this. So you end up with negative pi over 3. So this ends up being, what is sine of negative pi over 3? And then you have to remember your unit circle. So sine of negative pi over 3 ends up being negative square root of 3 over 2. So there's that one. All right. This one, that's kind of interesting. So after yesterday, what I'm hoping sort of sticks in your mind is anytime you see absolute value of something, right? Like the main point of yesterday, like one of the big points of yesterday, and even hinting from previous lessons, is anytime you see like x over absolute value of x, we get this picture, meaning as you come from the right, it's going to 1, as you come from the left, it's going to negative 1, and it doesn't matter what this is. The better way I like to think of this, instead of calling it x, I like saying, well, what if I have a happy face over the absolute value of happy face, where anything can go here as long as this and this are the same. And it doesn't matter if the absolute value is on top or the absolute value is on the bottom. But what we know is this, whenever we see it, is a 1, right? If we're coming from the right, it's a negative 1 if we're coming from the left, because we get this picture. All right? Now, how does that help us? Because when I look at this problem, okay, so when I look at this problem, it's like I've got, I'm looking at x squared minus 1 over the absolute value of x minus 1. I don't have exactly the same thing on top and the same thing on the bottom, right? I know how to handle it if these are the same. I don't know how to handle it if they're not the same. So what do? Well, you recognize that x squared minus 1 we can factor, and so this is really x plus 1 times x minus 1 over the absolute value of x minus 1. And now we have a situation where we have stuff over absolute value of stuff, which means this thing is either a 1 or a negative 1, depending on what direction you're coming from. So, if I'm coming from the right, okay, this becomes a big fat 1. Okay? If I'm coming from the left, this becomes a big fat negative 1. So what does that mean? Well, you know, if I were to look at the whole if I were to write this whole thing out, instead of just saying f of x, if I were to actually write it out as what's the limit as x approaches 1 from the right of x plus 1 times x minus 1 all over the absolute value of x minus 1. When I look at this, because I'm coming from the right, I know that this is a big fat 1. I just need to figure out what this is. So when I plug 1 in, 1 plus 1 is 2. So I get 2 times 1, and so this answer is 2. When I compare that to this thing, so if I were to write this out, I would say, what's the limit as x approaches 1 from the left? And I have my x plus 1 times x minus 1 over the absolute value of x minus 1. Because I'm approaching from the left, this becomes a big fat negative 1. And if I plug a 1 into this, I get 2 times negative 1, and so that gives me a negative 2. It's a little sneakier. All right, your turn. It's important. So, I'll go ahead and tell you what's important. What's important anytime you're graphing anything are your asymptotes. How do you know you have asymptotes? You have asymptotes anytime you see infinity, right? Like here, I see x approaching positive and negative infinity. Those are asymptotes. Here, I see, the y values are approaching infinity. That's an asymptote as well. So let's talk about these. First, anytime the y value is infinity, that's telling you have a vertical asymptote. And this is saying we have a vertical asymptote at 2. So at 2, I'm going to have to shrink this so I can fit everything in. Okay. So at 2, I have a vertical asymptote. And it's even telling me how the asymptote works. It's telling me as I go from the right, it's going to positive infinity. As I'm going from the left, it's also going to positive infinity. So I know that now I've got this picture. This, anytime x is going to infinity or negative infinity, it's talking about a horizontal asymptote. Here's a case where we have 2 horizontal asymptotes. As I go to the right, I'm going to a positive 2. And as I'm going to the left, I'm going to a negative 3. And asymptotes are in behavior. They're telling me where my graph ends. Now you could think, well, does that mean I do this? Maybe. We'll see. You might think, does that mean this goes all the way down here? Maybe. There might be some other things that are happening. The next thing we have are, we've got some limits. And limits are always more important than dots. I know it looks like these have the same information, but they don't. This just tells us where you have random dots. This is actually telling us stuff about the graph. See, this says, as I approach negative 1, I better go to negative 2. So as I go to negative 1, I go to negative 2. I'm going to put a hole here. And I know that the graph is, the graph's moving around. It's not just a dot. I have stuff around it. This is telling me the limit as x approaches 3 is equal to 4. So as I go to 3, this is go to 4. So I get a dot here, and we do this. Right? Actually, at this point, I am going to finish the picture. So to finish this picture, I know this is going to go down this way, and then this is going to go up. This is going to go up. This is going to go down. And then at the very end, I put some dots in. It says f of -1 is equal to -5. So at -1, I'm down to -5, which is down here somewhere. I get a dot way down here. This is telling me f of 3 is equal to 4. So at 3, that hole gets filled in. And there's my answer. I'll give you some more practice like that. I think I'll start Tuesday's class with another one of these. But if you can draw a picture from information, then that's going to tell me that you really understand what each of these things mean. So that's kind of a big deal. Problems that I've seen when I've given something like this on a test is people will create something that's not a function. Like it'll fail the vertical line test. I'll have people draw something up here and something down here, and it's like, okay. Or, they'll fill this in and put a dot. Well, if this is filled in and you put a dot down here, that's not a function because you have dots on top of each other, and that's a bad idea. All right, so what I gave you in OneNote is more practice on limits. You don't have to have it done by Tuesday. It's one of those things, look at it over. I'll give you some time in class to work on it on Tuesday. I also have some review problems from your textbook that I'll give you, so we'll work on that on Tuesday. And also the review problems, I've written solutions. So kind of the plan is Tuesday when we come back, we're gonna review, and is our test? Yeah, I think our test is still on Wednesday. So, but that's what we've got so far. We've covered everything with limits. Just kind of keep in mind our focus this year, because we have less time and we know it's just a weird situation. Until we get back into class, we're not going to focus that much on algebra. So you don't have to worry so much about the super tricky algebra problems. So we have to focus more on concepts. And this is a good example of concepts, because if you can get this information and draw a reasonable picture, you're showing that you understand exactly how limits are used to describe vertical, horizontal asymptotes, and even in this case, you're seeing how the difference between, right, you understand that a limit doesn't guarantee that the dot's there. This is an example of something being continuous, this is something not continuous. So there's that part. All right, any questions?